Why is it that some spectacular race car crashes produce only minor injuries? How can 3 collisions occur in this one crash between a car and a wall? The answers are determined by the laws of nature and can best be explained when physics meets biology. Through injury biomechanics, the study of the effects of forces on the human body, we've learned much about what happens in high-speed race car crashes, and doctors and engineers have used this information to build safer race cars and tracks. In a similar way, the study of injury biomechanics and crash testing has helped us learn what happens to the human body in passenger car crashes, and what works and doesn't work to reduce injuries and deaths in real-world crashes.
Hi, I'm Griff Jones. I'm a science teacher, and I'm here at the Insurance Institute for Highway Safety's Vehicle Research Center to explore the basic science behind injuries in vehicle crashes. So let's go behind the scenes and take a closer look at what happens to the human body in a crash. What is the first scientific discipline that comes to mind when you think of car crashes? It's probably physics, right? Because Newton's laws of motion govern what happens to a vehicle in a crash. But if we want to understand how crashes cause injuries to people, we need to look at what occurs when physical forces are applied to organs, tissues, and cells. This happens when physics meets biology in a field called injury biomechanics.
The Institute's Vehicle Research Center is a world-class facility for vehicle research and testing. A reporter described the crash hall with its 3 runways as a cross between a Hollywood soundstage and a NASA clean room. Vehicles are propelled down the runways at precise speeds, using a system of nitrogen-powered hydraulic motors and cables. The lighting array provides up to 750,000 watts of non-glare illumination for the 500 frames per second high-speed cameras. The research tests they're conducting here today focuses on how injuries occur in real-world crashes. This experimental crash replicates one in which a car hit a tree. In an attempt to understand injury patterns found in the occupants of the actual crash, researchers have disconnected the airbags.
Looking at the driver's chest, we can see the chest deflection reached about 50 millimeters of compression. The chest accelerations 70 to 80 G resultant acceleration range. High likelihood of skull fracture.
Very bad.
Yeah, very bad.
Figuring out what just happened in this test crash is the job of the research engineers here. Using sophisticated tools like instrumented crash test dummies, instrumentation in the car, and slow-motion film, they can analyze every detail and construct a precise picture of exactly what the vehicle and the occupants went through.
When research engineers use terms like the chest deflection reached about 50 millimeters, how does that relate to what a human occupant would experience? If chest acceleration is 70 to 80 Gs, which means that a force equivalent to 70 to 80 times the weight of the dummy's chest is pressing on it, is that survivable? How do these guys know the answers?
The search for the limits of human tolerance to forces began decades ago.
Today's race car and passenger car drivers benefit from biomechanics studies that were conducted during the 1940s, 50s, and 60s in the field of aviation, investigating how to protect pilots and astronauts from the strenuous forces of ejections and high-speed travel. Colonel John Stapp, a medical doctor and biophysicist in the United States Air Force, used himself as the test subject in his investigations of human tolerance to high G environments.
From the outside, watch the breakneck stop.
In one of his many tests, Dr. Stapp reached a speed of 632 miles per hour before one of the most powerful braking systems of all time stopped him in 1.4 seconds, subjecting him to more than 40 times the pull of gravity, or 40 Gs. His research helped establish the limits of human tolerance to high G environments and saved many lives through development and improvement of protective systems for ejection seats. Realizing the Air Force lost nearly as many men to car crashes as they did to plane crashes, Dr. Stapp began a car crash program using the rocket sled for seatbelt experiments. Human volunteers working with his biophysics research team endured as many as 28 Gs during safety belt tests.
This early research laid the foundation for the complex crash analysis that is conducted here today.
These dummies are a perfect example of combining science, technology, engineering, and mathematics to produce new tools that extend scientific understanding. They are the modern-day version of Dr. Stapp's volunteers. There's not just one dummy for VRC testing, nor even one type. There's a whole family of dummies for crash testing.
This is our crash test dummy family, ranging from a 6-month-old all the way up to a 95th percentile male.
95th percentile of what?
That means that it is larger than 95% of the male population in the U.S.
Wow, so this is a big guy.
Yes, if he could stand, he would be about 6'2", about 223 pounds, pretty big. The female, if she could stand, about 5 foot tall, 107 pounds.
How about the smaller dummies?
They're called crabbies.
Crabbies.
Are
they moody?
They're not moody, but it stands for child restraint airbag interaction.
And so when we're doing the frontal crash test, it's 50th percentile?
Yes.
Okay. Side impact is the small female.
Side impact dummy is a very complicated dummy. It has the most instrumentation. They have sensors from the head to the toe. The accelerometers give us the acceleration of the mass. The load cell measures force. And then we have the potentiometers that measure the displacement. The ribs actually move.
So dummies are very sophisticated. They provide data from many different body regions. But how do we connect this to people? What is the link between all these crash test data and the injuries that people experience in real-world crashes?
The dummy is measuring different things. It's measuring acceleration, force, and in some cases, distortion of the body parts. Those measurements can be compared against similar measurements made in experiments on biological tissues, using either animal models or cadaver models to get an idea of how much stress can this body part take before it breaks. So in order to understand whether or not a person would be injured, you need to know how strong the bones are, how strong the tissues are, and what conditions will cause them to break.
So the crash test dummies try to get a clearer picture of what's really happening to the people. Is that where the term biofidelity comes from?
It's exactly where the term biofidelity comes from. What biofidelity means is the characteristic of the dummy that represents how close to actually being a human being it is. So the higher the biofidelity, the more like a human being it is in representing how it moves, what types of stresses it measures in the crash test, and then the true-to-lifeness of those measurements to the prediction of injury in a real person.
This is how research engineers can tell us with precision what a human occupant would have experienced in a test crash.
Dr. Stapp's experiments, plus years of research with real biological tissues from cadavers and animals, have produced a set of reference values against which we can compare the stresses and strains the dummies experience. So we can measure these in a test crash and can figure out if they would cause injury to a human occupant.
But what do these stresses and strains actually do to people to cause injury?
Let's start with some basic anatomy. Your body contains over 100 trillion cells and is structurally organized into 4 levels: cells, tissues, organs, and organ systems. Tissue is a group of similar cells working together to perform a common function. Organs are made up of 2 or more types of tissue working together to perform a specific function. And each organ is part of at least one organ system that performs major activities or processes. Your body contains 4 fluid-filled spaces called body cavities that house and protect your major internal organs. Within the body cavities, your organs are suspended in fluid that supports their weight and prevents them from being deformed by normal movements. Your organs are also protected by your bones and muscles. For example, your heart and lungs are protected by your rib cage and sternum inside the thoracic cavity. Your brain is encased within your cranial cavity and is protected by your skull. Now, with this as background, remember the question from the beginning of this film: how is it possible to have 3 collisions in a single crash? Remember, the laws of physics hold true everywhere, on a highway, on a racetrack, and even inside your body. If a race car is going 200 miles per hour, so is the driver's body and every organ inside it. Let's answer the question. The first collision is between the car and the wall. The second is between the driver and the car's interior. And the third is between the driver's internal organs and the inside walls of his or her body cavities.
Tell me a little bit more about the injury.
To help us understand more about what happens to organs in the third collision, let's meet Dr. Stephen Olvey, a neurocritical care physician and director of the Neuroscience Intensive Care Unit at the University of Miami's Jackson Memorial Hospital.
Basically, during a crash, you have three collisions. You have the initial crash of the vehicle. Then you have the occupant hitting something inside the car and coming to a sudden stop. This results in impacts inside the body. For example, the lungs can hit the inside of the rib cage, the heart can hit the breastbone or inside of the rib cage, resulting in either a pulmonary contusion or myocardial contusion. This is what causes ruptured spleens, lacerated livers, because you have part of the organ well anchored and the other part is free to move about. And this causes a shearing force to take place in the organ, resulting in hemorrhage or tearing of the tissue. The brain is enclosed in a rigid case, the skull, and it's cushioned and surrounded by the cerebral spinal fluid. The cerebral spinal fluid is actually a different density than the brain itself, so in the event of an impact to the skull, the brain begins to move, the cerebral spinal fluid begins to move, but it moves at a different rate than the brain. So it will actually displace the brain in the opposite direction of the initial impact to the brain.
This simple experiment helps illustrate the phenomenon. This represents your skull. There's water inside representing your cerebral spinal fluid, and the red gel is your brain. The gel floats because it's less dense than water, just like your brain is less dense than your cerebral spinal fluid.
What do you think will happen to the brain during impact? Will it move forward, backward, or stay in the same spot? Let's see. The initial movement of the brain is toward the back of the skull. The more dense cerebral spinal fluid moves toward the side of the skull impact, displacing the brain in the opposite direction. If the impact is strong enough, the brain will initially impact the back wall of the skull, then rebound and hit the front of the skull.
This type of injury is called the coup contre coup, which is a French term meaning blow against blow. The order of events inside the skull is still debated in the medical community. Whether the more dense fluid displaces the brain in the opposite direction first, or whether the brain moves in the direction of the initial impact first and then is displaced by a wave of spinal fluid is not yet fully understood. By the way, this simple experiment was designed by a high school student for her science fair project. It was later published in a medical journal and has contributed to the debate. Crash injuries occur when stress develops in tissue. Another way this happens is when one part of the tissue or organ is firmly attached to the torso and another part is free to move. For example, with the heart and its blood vessels, the ascending aorta and its arch are mobile, while the descending aorta is fixed. Here's a demonstration of how a sudden stop, like a third collision, can cause an acceleration injury to the aorta. The aortic arch is represented by the unsupported gel. The gel inside the tube represents the descending aorta, which is fixed to the body.
Try to predict what will happen during the collision. The unsupported section of gel continues forward and tears away from the supported gel. During an actual collision, the fixed descending aorta will decelerate along with the body, while the arch and ascending aorta's momentum keep them moving forward. This difference in acceleration or deceleration causes a tear where the fixed and mobile parts meet. Even the inertia of a blood-filled heart can cause stress and strain on the aortic arch.
We've been talking about stress and strain on tissues and organs, and we've seen how a crash applies some of these forces. But what is stress and strain in this context?
Stress is a measure of the average deforming force exerted over a defined area of tissue. Stress produces strain, which is a measure of how much the tissue deforms as a result of the stress.
This special gel has elastic properties similar to certain human tissue, but not all human tissue is of equal strength. Forces and pressures on the outside of your body cause stress within your tissue. Three basic types of stress are tensile stress from stretching, shearing stress from opposing forces, and compressive stress from uniform compression.
Engineers judge the safety of a bridge by comparing the stress on the bridge to the strength of the building materials. Every material, whether it's concrete or different types of human tissue, has a critical stress limit. Stay below the limit and there is no damage or failure. Go beyond the stress limit and there is failure. Trauma to human tissue is like failure to a structure.
Here's a block of our special gel. A common type of crash trauma is blunt force, a non-penetrating type of injury from a body hitting a rounded or dull object, or vice versa. The impact produces a shock wave that moves through the body, similar to a sound wave moving through air.
I'm hitting this gel with a mallet, which will produce a shock wave that is visible in slow motion.
These waves change speed and/or direction as they move through tissues of differing densities, producing complex wave interactions that cause stress and strain in tissues and organs. Bigger and more concentrated impact forces produce bigger and potentially more damaging shock waves, thus more, potentially more damaging, stress and strain. If the type and size of the stress exceeds the strength of the tissue, then an injury occurs. But what exactly is it that shock waves do to injure tissue?
As shock waves move through tissue, they disrupt function at the cellular level.
You actually get injury to the cells themselves and they begin to malfunction. You get potassium, glutamine, and glucose leaving the cell, calcium entering the cell.
In a brain injury, this shift of ions within the brain causes the release of chemicals that can interfere with the brain's ability to regulate its own blood flow, and therefore its delivery of oxygen to the individual cells. This failed autoregulation, as it's called, can cause areas of the brain to become ischemic. That means they don't get the oxygen delivered that's necessary to function, and therefore they're at risk of malfunction to the point of cell death.
It's a chain reaction or a cascade of chemical events that takes place at the cellular level.
We've seen how injuries occur in crashes. High forces create shock waves, which in turn create stress that can cause tissues and organs to stretch, tear, or compress. This starts a cascade of events that can lead to cell death. So what is the key to reducing crash injuries? It's reducing forces on vehicle occupants.
Dr. Olby's day job is saving lives at the hospital. In his other career, he's a pioneer in the field of race medicine and chief medical officer for the Grand Prix Masters Racing Series. Dr. Olby organized the first traveling medical team in motorsports. Beginning in the early 1980s, he and his colleagues began collecting data related to race crash injuries in order to identify trends and methodically study injuries. In 1993, Olby's team began to use professional auto racing as a laboratory to collect and analyze data from onboard crash recorders. This led to significant safety improvements in race car and track design.
Now they have some innovations in the wall as well, so that the wall has some give to it.
It's called the Safer Wall, and it's a series of styrofoam plates behind the barrier that absorbs the shock of an impact, and it really cuts the strength of the impact by 40 to 60%.
You've heard about crash recorders in airplanes, so we have crash recorders in race cars as well. This box has triaxial accelerometers, which measure accelerations in 3 directions: vertical, horizontal, and longitudinally. So in the event of a crash, they can take the data off of this recorder, take it back to the laboratory, know exactly what the driver went through in that crash. This allows you to make computer models and reenact the crash, and you can make changes to the car.
Advances in motorsport safety, brought about by the study of injury biomechanics, have made a big difference in drivers being able to survive high-speed crashes.
He's going to unbolt himself from the 6-way harness.
Safety features like 6-point harnesses, rigid safety cages or tubs, energy-absorbing head surrounds, breakaway parts, and energy-absorbing walls have contributed to reducing forces on drivers and preventing injuries. In the vehicles we drive,
The study of injury biomechanics has contributed to huge improvements
in vehicle design. Many of these improvements have resulted from the work of the Vehicle Research Center.
The key here is
This is Adrian Lund. He's president of the Insurance Institute for Highway Safety.
you try to design the structure of the car so that it crushes in front, so you're bringing the car to a stop slowly over time. If you bring the car to a stop slowly, that gives you time to protect the occupants inside. So that's a little extra time for you to manage the occupants' kinetic energy. We have a good safety cage here. That means that there's plenty of room for the belt and the airbag to give them more ride down space. So even after the front of the vehicle has come to a stop, the safety belt can stretch a little further, the airbag will deflate, and they can ride that down. We're finding ways through our research to lengthen that amount of time over which these changes occur.
Here's a challenge I give my students. Design an egg-carrying car from only 2 sheets of paper but with unlimited amounts of glue. I provide the wheels and axles, but they must apply their science, knowledge, and skills to produce a crash-worthy vehicle that protects the egg. Ooh. The car with the most momentum that is able to protect the egg is declared the winner. Safe car. No injuries.
Now in a side impact, it's actually pretty hard to increase the time. So the other thing we do is to try to spread the forces over a larger portion of the body so that no part of the body experiences forces that will cause injury.
Right.
If you don't do that, then maybe the armrest just comes in and it hits you at once, and it's trying to accelerate your whole body just by pushing on your abdomen. And then you have injuries.
If you've got more force in a concentrated area, you've got more pressure. So you've got more stress and strain, which damages tissues and organs.
That's right.
Force and pressure are closely related, but they are not the same thing. Here's a more dramatic demonstration of the difference. Can you explain why the very sharp nails, trust me, they are sharp, do not puncture my skin? No, it's not magic. It is because my weight is distributed fairly evenly over the nails. The trick is to have a large number of nails. Pressure is equal to the force exerted on a surface divided by the total area over which the force is exerted. The more nails we have on our board, the greater the total surface area I am lying on, and the lower my pressure on any one nail. More nails means less pressure. We have so many nails on our board, we are going to put a 223-pound crash dummy on my chest. Even though the force has increased, there are still enough nails to keep the pressure at a safe, although rather uncomfortable, level.
It used to be that crashes were always referred to as accidents.
Accidents.
But that doesn't tell you how to prevent them. What tells you how to prevent them is to realize that this is a crash. It's a physical thing, it's predictable, it has predictable consequences. It's just the physics and the biology.
Whether it's on a racetrack, a rocket sled, or on the highway, the principles are the same. When forces are high on the occupants, there is potential for damage to tissue and organs. Keeping people safe in crashes has to do with extending impact time, keeping the occupant compartment intact, and tying the occupants to the compartment. What happens to the human body during a crash is determined by biology and physics. You can't argue with hard science. But what does stress and strain mean? God! Three basic types of stress are tensile stress from stretching.
Whoa! Upside down!
This happens when biology meets physics. Oops. And when physics meets biology.